Okay. So, is anybody joining for the first time today? Maybe, maybe you can raise your hand or speak up. I hope everybody had attended yesterday's class. Okay. So, yes, Satish. So yesterday, yes, do you have any question?
Yesterday I was absent because I was in train, so it
It's
is not
fine.
possible for me.
Yeah, sure,
And
sure, sure. It's
from today onwards,
okay. Okay, Satish, you can put your hand on. So yesterday we went over the logistics of the class. So maybe you can refer to the class recording. It is already uploaded on the IEEE portal. And from just and also yesterday we discussed upon the basics of EM theory. We did not start with FDTD, so we'll start with it today. So before we begin, anybody has any doubts regarding the class logistics? If we can discuss it now. I guess not. So we'll start with today's lecture. So today okay. There's a question in the chat. Okay, how long will these resources be online? Um, okay, so I am not sure about it. I'll inform you once I get in touch with the IEEE admin. Hopefully, this will always be there, but again, I'm not sure. I'll get back to you. Any follow-up questions? I cannot read your name. It's just written JG. So, any follow-up questions, JG? Okay, all right. So, on today's lecture, we'll start with the second module. We'll discuss some small topics which are related to the FDTD and start with the formulation. In today's class, we won't be looking at the code, but we'll look at the formulation needed for the okay. Okay, yes, Jay. So, so today's class will not do the coding part, but we'll look at the formulation needed for the electric field and magnetic field, which will be using it in code. So this at the end of the class, you'll see the snippet of the code which will be used in the actual FDTD, uh, the full code. Again, so those of you joining today, these are the textbooks which will refer throughout the course. And yesterday's class was based on the first two books by Cheng and Sadiku. And from today's class, we'll be following Sullivan and Davidson. We already went over these instructions yesterday, so maybe we'll skip it for today. Okay, so yesterday, for those who did not attend yesterday's class, we went over the basics of very quickly. Went over the basics of electrostatic fields, electrostatic fields, time varying fields, Maxwell's equation, boundary conditions, and potentials and harmonic fields, the wave equation. And for all these material, you can refer to these two books on your screen. Everything in from yesterday's class will be there in these two books. So today we'll start with module 2, and we'll start with the overview of finite differences. We'll discuss a little on partial differential equations, a brief history of FDTD, And then we'll start with the formulation for 1D equation, one dimension of FDTD. So, a brief history of FDTD. So, the FDTD, the finite difference time domain method, is a particular form of finite difference scheme. This was developed by Professor Kane Yi. You can see his photograph on the left side. Uh, so, these are based on Maxwell's equation in time domain. So FDTD is an explicit method. We'll discuss what explicit means. And again, explicit marching in time procedure. So we'll also discuss what this marching in time is. So using FDTD, we can easily simulate the propagation of electromagnetic waves and their interaction with the media around them. At, I'm sure right now one of FDTD is one of the most popular methods out there, and it is very popular also because of its simplicity. Like the formulations are very simple. You don't have to do a lot of computing for it. So after Professor E developed the FDTD formulation, it it gained more popularity after Professor Alan Taflov and Professor Broadwin obtained the correct stability criteria. We'll also discuss upon the stability criterias uh, for for this method and the steady state solutions using the finite difference technique. Again, the group of Professor Holland, Kunzenli, they applied this method for electromagnetic pulse problems. And finally, in 1981, Professor Moore developed a numerically stable second order absorbing boundary condition for this method. To We'll discuss upon the importance of the the absorbing boundary conditions. But in this course, we'll be limited to the first order absorbing boundary conditions. After following the lectures, you will be easily able to refer to text and implement the second order as well. And then again, in 1994, the Moore's boundary absorbing boundary condition is relatively less like it is good in for especially for first for 1D problems, but for second order for 2D problems, uh, uh, Professor JP Beringer introduced what we known as perfectly matched layer. So in the third module we sorry in the fourth module we'll look at the perfectly matched layer. Now CM methods can be implicit or explicit. So this is particularly relevant when one of the variables is time. So what are these implicit methods? So implicit methods require solution of a set of simultaneous equations. So in implicit methods, we have a set of equations, and we can form a matrix and use the we and by evaluating this matrix we get the unknowns. One of the popular methods out there, method of moments, is an implicit method. So over there, the the known is the one, if the unknowns, for example, uh, if you know the current density across the charge plate, for example, you can plot the charge density using it. So we won't have to worry about this implicit method. For this particular course, we will be using finite difference time domain method, and which is an explicit method. So in an explicit method, the value which we are looking for, that is for example, if we take a point in space and time, the current the next value at that point will is dependent on the not only on the past values of the surrounding point and the point itself, but also on the current value of the surrounding points. So also in an explicit method, we don't have to use any matrix. The value at the required point, the next value at that point, can be easily computed by using the values of at the adjacent points, the current values and the past values of the adjacent points. Okay, but the explicit methods also have their limitations. For example, like um, in an explicit method, we'll have what is known as a maximum time step. We'll discuss how we achieve this step, and if there is some discrepancy in choosing this time step, the solution can become unstable. So to keep the stability of this of the formulation, we'll be following what is known as Courant limit. So we don't have to right now worry about it. We'll discuss about the Courant limit and how we choose the time step uh, for this formulation. So we'll stop here and take any questions if you have. You can raise your hand and we can see if you have any questions, or you can type your question in chat. I hope I'm audible. Can anybody?
Yes, yes, you are audible.
Yeah. Okay, okay. So I guess no questions here. So in the last class, we discussed that the finite difference time domain method is based upon the partial differential equation in time domain. So these partial differential equations could be elliptic, parabolic, or hyperbolic. So these terms come from the conic sections, if you recall. This is although this won't be used further in our course, but it will be good to know what kind of partial differential equations we are dealing with. So this a simple partial differential equation in two variables can be given by this expression. So and for this particular partial differential equation, its discriminant can be given discriminant d can be given by AC time AC minus b square. So a and c are the coefficients of the second order derivatives, and b square is the 2b is the coefficient of the second term in the partial differential equation on the right hand side. And depending upon this discriminant, we know that whether the partial differential equation is either elliptic, parabolic, or hyperbolic. For example, a one-dimensional wave equation with its wave velocity as v can be expressed by this particular equation. And if you notice, the coefficient for the second derivative terms, the over here, a is equals 1 upon v square, and c over here is minus 1, and uh, b is 0 over here. So we get the discriminant as minus of 1 upon v square, which is negative. So hence this particular wave equation is hyperbolic. So most of the equations which we'll see in the upcoming slides for the wave equation in terms of electric field or magnetic field will be hyperbolic. Now, when we try to solve a partial differential equation, okay, there's a question. Yes, Jay, you can unmute yourself and ask the question.
Sorry, I'm not very strong in FDTD methods. In the previous slide, you mentioned that the wave equation is hyperbolic or parabolic, or what does this mean? The wave is hyperbolic or elliptic?
Okay, so the nature of this equation, when you if you plot the equations in so you if, like for example, if you have a partial differential equation, if you plot them in the on the axis, for example, over here, they are, the two axes are the two variables are x and y. So the plot you will achieve will be either an ellipse, parabola, or hyperbola. So, and if you know the nature of this curve, you will be able to approach a solution in a there are standard process to achieve solution. So for us, we don't have to concern with like the nature itself, but knowing what kind of equation will is good for what can I say? This will be good if you know what kind of equation you're dealing with, but this won't really affect whether your equation is elliptic, parabolic, or hyperbolic from the from the upcoming slides actually. So, any follow-up questions on that?
No, thanks. That's all right.
Okay. So you don't have to worry about whether even from the upcoming slides, even if you don't know whether the equation is hyperbolic, elliptic, or parabolic, you don't really have to worry about the formulation, which we'll be studying in the upcoming slides. Will be independent of whether what kind of these equation are. But just some if someone asks you that what kind of equation it is, okay, you'll be there to know. You'll be able to answer whether the given equation is elliptic, parabolic, or hyperbolic.
I thought it has something to do with whether something converge or not. So that's why I was maybe some like hyperbolic equation converge to some point at the local minimum. That's what I was confused, but that's all right.
Okay. So I'm not really an expert on that, but maybe I'll look into this and get back to you. Okay. Thank you for enlightening me. I'll look into this. But for the rest of this course, we don't have to worry much about it. Okay. Any more questions? Okay. Then we'll proceed. So for the partial differential equations, we have when we do it analytically. But for a computer to understand to be able to solve these differential equations, we'll have to use approximations. Now, depending upon which node we are looking for, this approximation could be either forward difference, backward difference, or central difference. So for a forward difference, by using the forward difference, the first derivative can be given by this particular expression, where the the two nodes involved are x plus delta x. At the two nodes involved are at x plus delta x and x, and the difference the spacing between the two nodes is delta x. Similarly, for backward difference, the first derivative can be given by this equation, where the two nodes involved are at x and x minus delta x. And using the central difference formula, the two we can find out the first derivative using this expression, where the involved nodes are at x plus delta x and x minus delta x. So we'll look into the derivation of the central difference formula in the coming slide. So all these expressions can be obtained by using the Taylor series. I hope everyone remembers the popular Taylor series taught in the undergraduate level mathematics courses. So looking at the derivation for the central difference formula. So if we do a Taylor series expansion about x uh, and evaluate it at x naught plus delta x for a function u, it can be given by this particular expression, where O of and del x power 5 denotes the fifth order terms, fifth order and higher terms. And again, evaluating at x minus delta x, we get this particular expression with. So both of these are Taylor series expansion, and when we add them, so when we subtract them and do a little rearranging, we can get the first derivative of the function u on the point x, and this will be dependent upon the values of u at x plus delta x and x minus delta x. I hope everyone was able to follow this particular derivation. Any questions on this? Okay, we'll move forward. So the formula for the first derivative, we saw that in the previous slide, that for the first derivative, it is given for the central difference, it is given in terms of at the points at x plus delta x and x minus delta x. Similarly, if we can, by adding the two Taylor equations, we can achieve the formula for the second derivative. So I will leave this as an exercise for you. Like uh, all the expressions are available in the previous slide. If you So the two equations on the top are can be added, and you'll get this for the second equation. But trying it by your hand, I think, will give you more confidence, I guess. Okay. Now comparing the three schemes. So for the forward difference formula, you can see for both the forward and the backward difference, you can see the error term is proportional to the cell length del x. Okay, so del x is the difference between the two nodes. Also, thus we will call it as the cell length. So it is proportional. So the both forward and backward difference formulas are proportional to the delta x. But in case of the central difference, it is proportional to the del square. Now, okay, sorry, there's a error over here. So for the limit del x tending to 0, the central difference formula will converge more rapidly to the true value of the derivative. Hence, since this central difference scheme is second order accurate, we'll be using the central difference scheme for uh, for uh, for the uh, for the approximation for the rest of the course. Okay, any questions on why will we using the central difference scheme?
And how this the last term, because O to the power 4 and 2 will affect the result in terms of central
No.
and back.
Yes. So the terms inside O del x power 4 are the higher order term. So basically, I've kept the del x square term out and shown you that the as the del x tends towards 0, it will converge. So basically, any del x term with a higher order will actually converge more rapidly. So the order of the error is dependent upon the on del x square. Similarly for the other terms as well. So essentially for the forward, backward, and central difference, I've kept one term outside, which is basically the order of the error. Did that answer your question? Any follow-up questions? Okay, so we'll move forward. Now, discussing upon the accuracy, convergence, consistency. How do we define accuracy? The degree to which a numerical solution to the numerical solution is able to approximate the exact solution. We define it as the accuracy. So we saw that the central difference scheme is second order accurate. So if you use a more higher order scheme, your results will be more accurate. But again, it will increase the complexity of your problem. For the consistency, so over here in FDTD, we saw that our scheme is dependent upon the cell length. So if you change the value of this cell length, your results will change. So if you use a finer mesh, that is this the smaller cell, your solution should uh, reach towards more, your solution will become more accurate. To check for convergence, what we do is we keep reducing the cell size and see how much the results are affected. So if the results bec- if we get the similar results by reducing the smaller size, and at some point you will realize that even after reducing the cell length, the results are not being affected much. So we at that point we assume that we have reached convergence, and with will and then we use that particular cell length for our codes. Now, for the stability, a computational program is said to be stable if any error introduced at any stage um, remains bounded throughout the code. That is, the error does not add up and accumulate to given erroneous result. So, for FDTD, the stability is defined by the Courant limit, which we'll discuss in the coming slides. Any questions on this particular about accuracy and convergence?
So here, I do not have a question on this one, but there is one thing I want to understand, which is not directly for this slide. For example, whenever I worked with CST, so they have asked one parameter called to define number of mesh cell per wavelength. Okay.
Yes.
So when we increase the number of mesh cell per wavelength, then we have a higher accuracy. I mean, the better result. And when we have a less number of mesh cells per wavelength, then we have low accuracy. However, when we increase it, then of course the complexity increases. So does it have something to do with this one, this delta X?
Yes, yes, you've
Okay.
got it very correct. Those also CST is based on technique known as finite integration time, which is very closely related to finite difference time domain, although not exactly. But again, also CST also uses square meshes. So which therefore the cell over there are also square. So you can specify this cell in for the number of wavelengths. And if you increase the number of cells per wavelength, you will be better able to approximate the waves, and hence you'll achieve more results. But again, the since you're increasing the number of cells per wavelength, the number of total number of cells in your simulation space increases,
Right.
which will increase the complexity and the total time taken by your simulation. So
Hmm.
what is a general practice I think we do is we keep refining, we keep changing the cell length to and see whether how much and the correct like how much variation is there in the result, and then we choose I guess a cell length which gives us a good result in a given time.
Hmm.
Like,
And just now,
was I able? Yes. Any follow-up questions?
and just now you mentioned that when the length of the cell is low, then we have a high convergence. What does this mean?
Okay. So if we go back to the this particular, if you can see the central difference equation, so the error term is directly related to the mesh size, that is the cell length, the delta x. So if this delta x is small, we the central difference scheme will converge more rapidly. That is, the error will be small. Since the error is directly proportional to delta x, the error, if the delta x is small, the error will also be small.
Okay, all right, thanks.
Okay. So, while approaching a problem in like how we go about using the finite difference method, so first what we do is divide our simulation space, or that is our region, solution region, into a grid of nodes. So we over here, and will be use will prefer to use since this particular uh, module is for one dimension. For us the cell length is essentially a small line segment. So we pick points at which we define the electric field and magnetic field. Now then we saw that we can approximate the finite we can approximate the differential equations using finite differences, and we find out the value of this the we find out the value of the electric field and magnetic field at these nodes. So to solve a finite difference equation for a solution at each node, we will have the solution is subject to the boundary conditions and in the initial conditions. So for the boundary conditions, we'll wait for a few more slides to then we'll go towards the absorbing boundary conditions. But for the initial conditions, we'll need some source. So and since we are operating in time domain, the values at the next step will depend upon and this is fine. This is the FDTD, since it is an explicit method. The values of the next nodes will be dependent upon the values at the previous time point and the surrounding nodes. So these values when we calculate for the next node, this is known as the time marching. So when you calculate the value at one particular time instead of one node, and then this particular value used by the next by the next by the same node at the next time instant. So what you do is you march in time. uh, this will become clear when we go about updating finding the update equations for E and H. And this time marching in the context of what FDD is called leapfrogging, because we jump from one node to the other to calculate the values. So this particular the solution process will become more clear as we go about uh, studying the different updating the things required to write down the code. And once we go toward the formulation of the code, I think you'll get the gist of what these three steps mean. So for it, now we'll start. Okay, there's a question. Yes, Priyank.
Hello. Is I'm audible?
Yes, you are.
Yeah. So I have a question. Like in Maxwell equation, we have the discretization in time domain or as well as in the space domain. So here in FDTD, are we doing the discretization space and time domain both, or simply in time domain?
Yes, in both. We'll come to that in this slide and in the upcoming slide. So we'll discretize in both space and time.
Okay, because the name FDTD means like finite difference in time domain. So that's why means
Yeah.
it should be also some space domain also. No, nothing like that.
So it is actually implicit that we are discretizing in space. So all the methods, I believe, discretize their solution, the solution domain in space, and then whether do you use a frequency domain technique or a time domain technique. So when we say the time domain, so it refers to that the problem is being solved in time domain. And the finite difference part actually refers to that we are using finite difference approximation in this method.
Okay.
Any follow-up questions, Priyank?
No, thanks.
Okay. Any questions? Anyone else? Any questions up till now? Okay, so now we'll start with the formulation of update equations for electric field and magnetic field in one dimension for finite difference time domain method. So the Maxwell's curl equation for free space are given by this particular set of equations. And for this particular module, since we are doing it in one dimension, we can write these two equations simply as in terms of Ex and Hy, and the so the electric field's orientation is in the x direction, and in these equations, and the magnetic field is orientation is in the y direction, and the wave is traveling in the z direction. So we'll be using this. Let me get my pointer. Okay, so we'll be using this particular equation from in the upcoming slides. So over here, this set of equations are actually in 3 dimension, and for 1 dimension, we can write them over like this. So the next step will be taking central difference approximation for both time and space. Okay, so to answer your question, we'll just go back. We'll do the central differencing in space and time both. So we saw that this is the formula for the central difference scheme, and we have our Maxwell's equation over here. Now taking the central difference on both, we get this particular set of equations. So you don't have to worry about it now. In the next slide, we'll discuss how we got this. But uh, you have to remember that over here this n refers to the this n refers to the time step. Okay, so for any instant t, we represent it as delta t times n. So delta t is the time step, and n is the nth instant in nth instant, and the product is basically the tth time instant. So if the n is one time instant, n plus 1 will be one time step later. And the terms in the parenthesis, that is this k is the discretization in space. So taking the cell length as delta x, and the product delta x plus k is basically the zth position. So k is the kth node in this solution space. Okay, so now what taking the central difference scheme for the electric field in time domain, we get this particular expression. So what we are trying to do is we are trying to find the electric field at the kth kth node, at the kth node, and so what we do is for the kth node, we take the since the since the difference is in time, since the derivative is in time, so we take the electric field values at the n plus half position and n minus half position. Now, why we are using n plus half and n minus half? So this is this, but Priyank, do you have any question? I can see you are unmuted.
Sorry, I by mistake.
Oh, okay. So this particular convention this will be following is that the electric field will be defining the electric field at the points for example, n plus half, n minus half, and similarly n minus 3 by 2, n plus 3 by 2. At these points, we have defined the electric field, and in between these points, we will define the magnetic fields. So the magnetic field will be defined at the time instance n plus 1, n plus 2. So what we this and this will become more clear when we see the total update equation. So over here, when we are trying to find out electric field at the kth point in space, and that since the difference is in time, so we take the electric field value at a previous time instant, that is n minus half, and at a time instant next to it, that is n plus half. Similarly, for the magnetic field, we are trying to find out the magnetic, since the derivative is in space, we take the magnetic field value at the time instant n. We take the magnetic field's value at the k plus half and k minus half nodes, and so we get this particular equation. So uh, is this clear? Like, do you have any questions? Yes, yes, Vivek.
Yeah, sorry, but I am unable to understand why you are taking this n plus half and n minus half.
Okay, so what we are trying to do over here is we need the electric field's value at a kth position. Now at kth position, okay, so this particular red line is the kth position, okay, and these are the time instants. So if we need the electric field value at this kth position for nth time instant, what we do is, so we want to find out what the electric field is over here. So what we do is we take the electric field value at n minus half, n minus half and n plus half, and we will use this. We will get the value of electric field at this particular point. But essentially, this particular value will be used by the magnetic field when when we equate these two equations. And I'm sorry, but this has been the convention that we use n minus half and n plus half. You can use n minus one and n plus one, but this is more of a convention than and then so I do not have a really good answer to this, why we are using half and half values, but this is how we have this is how we discretize the space in finite difference.
Okay, so can I say it is a kind of averaging you are taking?
uh, Averaging would be when we divide it by like 2, but since this is a derivative, we are dividing it by delta t. So if averaging helps you get an understanding of this, yeah, sure, but this is not exactly averaging. This is taking a derivative and using the central difference scheme. So this, in the central difference scheme, what we saw that we can get the value at a particular instant by using a value at a previous node and at the next node. Since over here this is in time, so we are taking the value at a previous time and at the next time, at the previous time instant and the next time instant. And from that, by using the central difference scheme, we are able to get the electric field at this particular nth time instant. Was
Okay,
I
got it. Thanks.
okay? So similarly, since for the magnetic field, this derivative is in space, so we are taking the value at the this particular node, for example. So we are trying to find out the magnetic field at the kth position at the nth time instant. So we use the values at the k plus half and k minus half. So now that we have the derivative, this derivative of electric field and magnetic field in terms of the central difference, we put them in this equation, and so we achieve the electric field and magnetic field, the Maxwell's equation in terms of the central difference scheme. Now similarly for this second Maxwell equation, we again we since now the magnetic field is the derivative of time, we take the Maxwell, we take the from that central difference in technique. We are trying to find out the value of the magnetic field at uh, k plus half position, and for that we find we take the value of magnetic field at n plus 1 and nth position, and by using this particular values at this particular these two time instants, we are able to get the magnetic field value at the uh, n at the n plus half position. And now, and similarly for the electric field, we are trying to find out the electric field value at the k plus half position, at the k plus half position. We take the value of the electric field at k plus 1 and kth position, and by using the central difference scheme for this space derivative, we get the value of the electric field over here. So for the electric field, to find the value of electric field, we use this particular node and this particular node. And for the magnetic field, to find the value of magnetic field over here, we use this particular node and this particular node. And once we get this, the two derivatives in terms of central difference, we put them in the Maxwell's equation, and then we get the second Maxwell equation in terms of the central difference. So will wait over here. Since this is very crucial for the next step. Okay, there's a question. We take the difference of half in time, while we take the difference of 1 in space. Is there any specific reason? So actually, we are taking the difference of half in both space and time. So you can see we are taking the difference of half. The difference taken is actually 1. Okay, so whenever there is if you see the indices, so if there is a k plus half over here, okay, so if there is k plus 1 and there's k, so there's a difference of 1. And the previous slide, if we go, so if there is a k plus half over here, there's a k minus half. So essentially, the discretization is still remains either delta x or the delta t. But we define the point such that we are able to calculate the magnetic field or the electric field at that particular point. For example, if we saw over here that we need the value of we need the value of okay, so we need the value of the magnetic field at the kth okay, at the kth position. Okay, we need the value of the magnetic field at the k plus half position. Where is that? Okay, so over here, this time instant, this space instant we are talking about. So we are taking, we need to find out the value of at the k plus halfth position. So we took the average and at what time instant? At n plus half instant. That is why over here we have n plus 1, and over here we have n. So when we find out this particular so over here, this particular hy will find out at n plus half time instant. Okay, I think I made it more complex. What we are trying to to answer your question, the difference always remains either delta t or delta x. We are just defining points at either halves or at whole values. Was I able to answer your question? Maybe I can try it again. Okay, so once we got the Maxwell's equation in terms of the central difference scheme, we'll now rearrange it to make it usable for us. So here are the Maxwell's equation using the central difference scheme. So we started from we started from this particular set of equation, and now we have obtained this equation. Sorry, this should be 1.5. Okay, so now that we have this particular set of Maxwell's equation central difference scheme, we will rearrange rearrange it and simplify, so that we get the electric field at the n plus halfth position, which is the latest instant. Okay, so n plus half is the latest instant, and we can rearrange it such that the electric field value is dependent on a previous instant, that is n minus half, and the magnetic field's value at the at a half previous instant. That is, since the electric field is at n plus half, the magnetic field values are at n a time instant, and they for which locations the k plus half and k minus half. That is, the electric field is can now the electric field at the kth position at n plus half instant of time can be given in terms of electric field at the same at the same point at a previous time instant, and magnetic field and the value of magnetic field near the surrounding points from a previous time instant. Similarly, after rearranging the second equation, we can express the magnetic field at the latest time instant at k plus half position in terms of magnetic field at the same position but at a previous time instant, and the electric field at surrounding nodes at a previous time instant. Now, using this half thing, we can see we are able to visualize better that the electric field is being computed from a nearby point. But if this point is very closer to this very is very closer to that particular point, so we can say that the at a very close time instant, we are formulating the we are able to we are finding out the magnetic field in terms of the electric field from a very close point at a very same instant. Okay, so using from these two equations, we notice that the calculations are interleaved in space and time. Like you can see that for finding the values, we need to calculate for finding the electric field, we need to calculate the electric field at a previous instant in time, and also by the nearby point, which is at the nodes in the nearby space. So this is the fundamental thing for the finite difference time domain. So this is very crucial, and this will help us in developing the update equations. So if you we'll pause, and maybe you can look at the equations, and if you have any questions, we can discuss.
Hello.
Yes, Priyank.
Yeah. So first equation, yeah, I am easy to absorb the first equation, but second equation means, can you a little bit explain again second equation, like the bracket part of this electric field means here the time is, I'm not getting it is the previous time or at the same time in second equation for electric field, or in space term it is the previous time or the next time. So means I'm a little bit confusing in the second equation. So can you repeat means what you tell about second equation?
Okay, so what we did was in the first equation, you were able to follow the first equation, right?
Yes, yes.
Getting the yeah. Okay, so over here you can see we need the magnetic field to get the value of the electric field. We need the value of the magnetic field at k plus half and k minus half instant. So basically, we need them to be at this particular at this particular nodes. So for the second equation, instead of doing it at the same time instant, we found out we express the magnetic field at this particular node, and use the half difference of time. Now, using a half difference of time actually simplifies our problem. This might seem complex now, but once you get the notes, if you try to use a pen paper, I think I'll highly recommend using a pen paper to obtain this particular set of equations. You'll be able to express the magnetic fields at this particular points in terms of the electric field at the values. So we will be able to express the magnetic field at this particular instant, at this particular points, in terms of the electric field. So now, so essentially, what is happening over here is you need the magnetic field values to express the electric field values, and you need the electric field values to express the magnetic field values. Now, the second equation, I know it will seem complex, but it was necessary to derive it in terms of k plus half, because in the first expression we are finding out the magnetic field at the half instants. But once you get this particular equation, sorry for this typo, this will be 1.5, which is basically n plus this will be this should be point yes 1.5. I no, this should be half, I believe. Yeah, 1/2. This should be 1/2. There's a dot over there. So this will be n plus half. This should be also be n plus half. So once you get these two equations and you simplify, you keep the this particular term on the left hand side and bring all the terms on the right hand side, you will get this equation. And for the second equation as well, you keep this term on the left hand side and you bring all the terms to the right hand side, you will get this equation. So now you can see, once you if you take an initial value for the magnetic this for the electric field and the magnetic fields, you will get this particular electric field value. And similarly, you'll be able to use this electric field values to update the magnetic field values. And this is how you'll be able to run your code. That is, the magnetic field values will be then calculated by the electric field values and the magnetic field values from the past instant, and then the electric field values will be calculated from the magnetic field values of the past instants and the surrounding nodes, and the electric field values from the past instants. So basically, these are interleaved in space and time. So that is what I'm trying to like explain. Like, were you able to follow like what I explained right now? You any follow-up questions?
Yeah, actually in first equation means by looking at the equation, it is easily like gettable. Like the electric field is in the
Yeah.
Nearby points, and magnetic field in the nearby points in space, and electric field in time domain. So it is n plus half and n minus half, whereas in magnetic field is a k
Yes.
plus half and k minus half. Whereas in second equation,
Yes.
it is not easily
Yes.
gettable. Like it is not the nearby points means like here, if you look at, it is in time domain, okay, it is n plus 1 and n, whereas in uh, when you look at the electric field, it is in okay, in space it is again the difference of space, but time is also why the time is not same, it should be n plus 1.
Okay, I get your problem. So what is happening is you can understand the first equation, but you are thinking you can see that h is h is being calculated at nth time point, and similarly the e is also being calculated at the nth time. Okay, but in the next equation, what we have done is we are trying to calculate the magnetic field at the n plus half a point half a time instant. Okay, so why we are doing this is because we in the first equation we already it is like, if you see this particular equation now after rearranging, so what is happening over here at this right hand side should it is already known to us. So we already know the value of magnetic field at the nth time instant for k plus half and k minus half. Okay, so what we now need is the magnetic field values at the next time instant. So for that we use this particular so we calculate we so we chose the we tried to we wrote the equation for n plus half a time instant for the electric field, where we uh, because from this equation we'll be able to calculate the electric field at the n plus half instant. Now this
Okay, okay, I
magnetic
got
field
it. I
has
got it.
been
One point.
okay.
Yeah, yeah.
Yeah,
Actually,
so
in the
this
second equation, the electric field is a word that we got from the first equation, right?
yes.
Okay.
And now what will happen is when you as you keep adding terms to it, for example, this first equation, if you add one over here to, so this will become n plus 3/2, and this will become n plus half. So you will and this will become n plus 1 and n plus 1. So you will already got this value of n plus 1 over here, and so this equation will be run after this. So while coding, you'll first run this equation, and then run this equation, and similarly then again you will run this equation. So and this is how you will be able to calculate the value of electric field and magnetic field at every time instant.
Okay, I got it. Yeah.
Yeah, any questions? Because the next slide will move towards the how we implement this in MATLAB or Python. We'll just see the snippet. I'll give you some time. Maybe we'll wait for some time, and you can look at the equation and if you have any questions. Okay, so we'll proceed. So now we have already found out, like we have already obtained the update equations using the central difference scheme for the electric field and magnetic field at the different time instants. You can notice now that both the equations are very similar. Okay, they're very similar apart from this coefficient. So to make our computation simple, okay, so what we do is we use a change of variables, and we uh, uh, we make a change of variables and we multiply them with this particular coefficient. And so we what we achieve over here is both the equations will become same, uh, very similar, and you'll just have this particular coefficient for both magnetic field and electric field. uh, this is being done just to make the computation simple, because electric field and magnetic field, they differ by several orders of magnitude, and to reduce the errors which might be introduced because they are in they differ in several magnitude, and to make our computation and this formulation simple. So what we do in the next step is we just replace this coefficient by one particular value, and then we get the update equations, which are very simple. So this does not affect our formulation. This is just a scaling factor, so we don't have to worry about. But since this will come up in the update equation for MATLAB and Python, it was necessary to clearly state it. Now, you should recall we simplified this the coefficients to get this particular value. So now in the coming slides see how we choose the cell size. But for now, if we like we all we have this we know that we have taken a particular cell size as delta x. Now how do we calculate the time step? So the time step can be determined by this particular equation, and again this is calculated by using the Courant limit, which will come again in the upcoming slide. But once we have the cell size, we determine the time step from this equation, where c naught is the speed of light in free space. So we are our computation right now we are formulating it for free space. So we have already got the update equation for electric field and magnetic field, but the unknowns over here in the previous equations, where we did not know what was the delta t and delta x. So right now, so we have chosen a delta x, and from that delta x we have calculated the delta t. So so now we have obtained all the variables, all the values for this update equations. And now by substituting this particular value of delta t in the coefficient, we simply get this simplifies to as half. Okay. Now introducing this half over here. So this particular coefficient is simplified to half, and then we can simply write it in for the computer. We can write it in this form. So ex is being defined at the kth space, and similarly the we have the magnetic field values that since the computer only understands either whole numbers or natural numbers are there as their index to their array. So we have add so we'll what we do will add half to all the this coefficient like this in the subscripts and superscripts. So by adding half, we get this. A minus has been taken out over here. This was minus and this is now plus. So we get the electric field in terms of the magnetic field and the electric field at the previous instant. Okay, so there might be one confusion since we are not storing the variable in time. So there is just one index to array. This is a linear array in one dimension. So the previous so over here what is happening is this electric field is at a previous time instant, and from the magnetic field at the nearby points, we get the value of the electric field at the current time instant, and we update it. We are not storing the values over here. That is why we do not have the variable of time, and the time is being controlled will be controlled by a loop outside. So we'll pause over here. We'll take questions. Any questions on how this particular equation got translated to this? This is something which you write in MATLAB or Python. So I hope, like in the last survey, class survey, I noticed that everybody was somewhat familiar with MATLAB. So I hope this is something you understand writing in MATLAB. And this is written from this particular equation, and over here the coefficients have been simplified by half, and this half what we got was decided by the calculating the time step in terms of the cell size, and the cell size was already known. Now how we knew that, we'll discuss that in coming slides.
Okay, looks like in the coding it's much more simplified and easy to understand, like one time instant and the previous time instant and next time instant. So
Yes, and coding it really does become very simple, but by formulating it was necessary to use the halves because it would be okay. I guess there was an echo. So if we use the current time, if we use the values of the electric field and magnetic field at the same points, it becomes really difficult to understand. So what we do is to view it more as a holistic. We assume that the electric fields and magnetic fields are being calculated from the nearby values and in the space and both in time. So it gives a more clearer understanding. So I think I think right now it will be difficult to follow for the analytical formulation what we did earlier, but maybe going through the slides and doing running a bit of code maybe will give more clarity to it. So any questions regarding the how we implemented this particular update equation to this MATLAB or Python equation? Like I think everybody's familiar with this particular set of equation. Okay, so because we'll be using this equation in our code, and it is very essential that you know how this particular equations were like found out. So that if you when you implement your own codes, you should know what how do you obtain those equations so that you can modify them accordingly. But again, you don't have to worry much about it right now. Once we are done with this course, I think you will be at the end you will be able to better and get a whole picture of how we went through, and going through the slides will make it really easy. Okay, so up till now we have got the update equation for electric field and magnetic field. And we know the time. We have we have assumed a particular cell length, and we know the time instead the time step we are taking. So we could move to the simulation, but what will we simulate, because there is no source, because there should be some excitation which will generate a particular wave, and then we'll be able to see Okay. Are you guys able to hear me? I think I lost you for a second. Hello.
Okay.
Am I still audible? Can you tell me? Were
Yeah,
you
it's
able to like?
yeah, everything's fine.
Okay.
Everything's fine.
Okay. Okay. Because it was showing me that I was disconnected. Okay. So up till now we have obtained the update equations for electric field and magnetic field, but since but and if we even if we start we write our code and try to simulate, we won't see anything in our anything going on because we don't have any excitation. So to include an excitation, we'll study more on these different sources, but right now to see a particular result, because it is very essential that we see some results so that we can like gain some trust. At least you can get some trust on me, like what I'm teaching, you'll be like it will amount to something. So I'm introduce like for now we'll just look at the Gaussian source. A Gaussian pulse is very popular in finite difference FDTD simulations. Its expression is widely known, and the interesting thing about the Gaussian source is that it is same like its spectrum is same as again a Gaussian pulse. It only gets scaled according to the mean and the deviation. So we'll be using this Gaussian source. Introducing how will we include this Gaussian source? We'll discuss in the next lecture today. So you just to emphasize that this is how a Gaussian pulse looks like. We'll be giving this particular excitation. We already have the update equations for electric and magnetic fields. So we'll see some results now. So I simulated, I wrote the code only based on the information we have discussed till now, and a few slides from the next class. That is how we calculate the delta t, how we get the delta x, and the Courant limit. So up till now, whatever we have discussed will be we are implementing it. So and using a Gaussian source, including a Gaussian source or any kind of source is not very difficult. It is really easy, but we'll discuss it in the next class, because throwing too much information might only cram you and not if you won't be able to follow much. Okay, so on the left hand side, I'll start the this particular simulation. So I introduced a Gaussian source at the center, and the pulses the based on the E and H update equations, the pulse travels to both the directions. Now what happens over here on the boundaries is that we have not included proper boundary conditions, so they get reflected from the boundary, since our the whole simulation space is very small and the waves reach the boundaries very quickly. In the next class, we'll also discuss the absorbing boundary conditions. So you can see this particular simulation where I have included the boundary conditions, and the same Gaussian pulse excitation will travel to the boundaries, and will have very minimum reflections. The reflections are of very small order, so you won't be able to see much on the screen. So these are the two results which I wanted to share with you, so that it will keep you motivated for the further like the next class. Um, okay, so any questions till now or throughout the? So this is the last slide that we'll discuss today. Any questions from the previous slides and what we discussed right now?
In this slide, where is the boundary condition? Is along Z or along EX? I mean, can you please say a few more things about the boundary condition here? How it is?
Okay, so what happens is we found out we looked at the electric field and magnetic field update equations, and we assumed that we knew the previous instant values. But over here, what happens is we have assumed that at the initially they were zero. So what happens is at the boundaries at the yeah, so at the left hand side of the boundary, the electric fields values seem to be 0, and on the right hand side the magnetic field values become 0. So the Gaussian pulse reflects with a positive phase or a negative phase, so like that. So essentially the boundary conditions have not been involved, and the boundary conditions are in space over here. So what in the right hand simulation, and basically this particular, how do I remove this pointer? I can't. Okay, maybe bring this. Okay, so essentially the boundary conditions will be imposed on over here. So this is a simulation in 1D, and what you're seeing over here is the magnitude of the electric field at in these particular points, and the boundary conditions will be included in space on the edges of the simulation space. Was I able to I can any follow-up questions so that I can explain it more clearly?
Okay, I got it. So boundary conditions defined along the Z at 0 and 5, and the electric field is changing so at these 2 points based on how it is defined.
Yes, yes, yes.
Right.
So over here, what and in the next this simulation, so the boundary conditions have been included, and these boundary conditions are essentially numeric. So what we do is we numerically match the values at the ends so that we don't get reflections from the boundaries, because while simulating an object, we don't want reflections coming from the boundary. For example, if you like the antenna engineers or if you work in microwave, you must recall what we have is we have an anechoic chamber. So what we do is we do not want reflections from the we try to simulate an like open-ended environment so that we don't have reflections from outside. So similarly, that for that purpose, we will have to include the boundary conditions because they are not implicit in finite difference time domain method. So in the next class, we'll look at the how we okay. So next class we'll discuss on the boundary conditions. So today, like to recapitulate, we went through the we went through something about the partial differential equations. We saw the approximation using finite differences. We discussed a little about the implicit and explicit methods. Saw a brief history of the finite difference time domain method. We discussed a little about the accuracy convergence. This will come up again in the coming slides. Um, uh, oh, there's a hand over here. Okay. Yes, Shri Prasad. You can
Yeah.
unmute yourself and ask.
Okay. Hello, sir. Actually, I have a doubt in the simulation results you just showed. In the left figure,
Okay.
you like in the left figure when the electric field is getting reflected, one part is going down, like going negative, and the other one is simply the same. So why is that?
Okay. Right now, I won't be answering this question. So once you get the codes and you simulated yourself, I think maybe we can discuss on this, like why this is happening. On one boundary it is getting reflected differently from the other. So I won't
Oh,
answer this question right now because if you are able to find out this answer by yourself, I think you will be amazed. You will impress yourself. And if not,
okay.
we'll discuss it in class.
For sure. Thanks. Yeah.
Okay, so we looked at the basic procedure of FDTD. Don't have to worry about it. Since we will discuss the whole process in this course. We did a little simulation. We saw some results as well for the FDTD simulation, and I think you guys will also be excited to do the simulation by yourself. In the next class, we'll discuss a little about the stability and the FDTD method. We'll for sure discuss about the absorbing boundary conditions. And in today's class, we discussed the formulation in free space. We'll include a dielectric. We'll see how we do formulation for a dielectric medium, and we'll look at simulating a few different sources. For example, Gaussian, sine modulated Gaussian, maybe a sine source. So we'll look at those topics. So that will be all for today. Again, I'll wait for there are some hands over here. Okay.
Yeah.
Uh,
So it's here. I have one last question here. On the source
yes.
excitation slide, you mentioned about Gaussian source. So is there any specific reason to consider Gaussian wave? And is there any other types of possibilities of kind of waves to consider as a source?
Yes. Okay. So to show the results, like because I have for today I've included only Gaussian source. We'll look at a few more sources. I'll discuss 2-3 sources, and then I have also recommended the textbooks. They have more different types of sources. For example, differentiated Gaussian and different sources. So each type of excitation has their own merits and demerits. I think referring to the text will be the best. And over here, there was no particular reason for my side for using Gaussian. I could have used sine modulated Gaussian or a sine source, but to show you these two results, it would have been really difficult if I was using a sine wave, because upon getting reflection from the boundary, uh, the 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 visual thing won't be there. There will be too many standing waves will be happening over here. So for today's lecture, there was no particular bias or any particular reason for using a Gaussian source. We'll discuss the different types of sources. And once I tell you how to include a Gaussian source, you will be able to include any source of your like how you like. Any
Yeah.
question?
Okay.
Any
Okay.
follow-up
Thank you so much.
questions?
No, thank you.
Yes. Shri Prasad, I can still see your hand still raised. Do you have any questions?
No, 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 no. I will.
Okay. 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 That was all for today. We'll wait for few more minutes, so that if you have any questions, you can recollect, or we can all and if you have any questions regarding the logistics of the course, for example, timing or course material, your login ID, password, if anything you have you have any issue, we can discuss now. Yes, Abhishek, you can unmute yourself and
Hi Anand, thanks. I haven't received my login ID password from IEEE. I've mailed you also.
oh, okay. Yeah, I got your email. I've contacted the admins. I guess since this is weekend, they are not in office. I have not received a response from them. But I'll make sure that you get the login details from in the next week. I'll try to push them to do this.
Thank you so much.
Meanwhile, I'll be simultaneously uploading the class notes on my website as well. You can get the lecture, the slides over there. And I have been asked not to upload the lecture apart from the IEEE outside IEEE portal, so I won't be able to do that. But you'll get the login ID, so you don't have to worry about it.
Sure, thanks.
So I think today's lecture is like
Okay. Any more questions? We'll wait a few more minutes.
So I think today's lecture is the backbone of all the future lectures, because, and I guess as I see the course outline, so in the future we are going to analyze um, the selection of the sources and how it behaves with respect to different boundaries in 1D simulation, 2D simulations, and 3D simulations, isn't it?
Yes. Yes.
Okay. Yeah.
So coming back to the course outline. So right now we are going a little slow, and because we have to introduce many topics. So right now we are just over here. Okay. So at this particular point, are you able to see my screen?
Yes. Yes.
Okay. So right now we are just over here, but we will move very quickly through these topics because they won't take much time. But what we discussed today, essentially the formulation of electric and magnetic field is the most important one, because that will remain constant throughout even in 2D, 3D, they will be same. We'll just use more Maxwell equations for different dimensions, and the same central differentiation technique will be used. And this includes the inclusion of this dielectric medium will only affect the mu and epsilon. Similarly, for frequency dependent media, will just shift from electric field to electric displacement. Uh, 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 that is from E to D will shift. We'll see why we do that. And and some more time will spend on this perfectly matched layer, because for 2D and this is very important for doing 2D and 3D simulations. So right now we are over here, but we'll try to cover more in coming lectures. And again, I'll like to emphasize, please try to get these particular textbooks, and this will be really helpful for you throughout the course. Especially this Dennis M. Sullivan. Like, this book is really good. I highly recommend it to anyone who's starting with FDTD or already knows FDTD. Excuse me. The Bangalore's weather has not been kind to me. Any questions? Any further questions? And then we'll close. Okay. Meanwhile, I'll stop the recording.